So welcome to another DSG seminar. Our speaker today is Xiangyao Yu from University of Wisconsin-Madison. Xiangyao has done his PhD at MIT, and then he stayed there for a postdoc period, and then he's been at Wisconsin-Madison for a few years, and his work focuses on cloud native databases, new hardware, and really core database technologies. Today, he's going to talk to us about his work on GPU databases. Jiang Yao, I'll leave the floor to you.
Okay, thank you so much, Damer, for the introduction. Hello, everyone. My name is Xiangyao Yu. So today I'm going to talk about some of our recent work on GPU databases. We have been working on this for a few years, and we truly believe this is really promising technology. It may become the new modality of data analytics in the future. So hopefully within a few years, we will see GPU databases being widely deployed in practice. Okay, so here is the structure of my talk. I will first talk about the hardware trend for GPU. I don't know whether you have heard of this in the previous talk, but I'm going to present this from my own perspective. So hopefully this gives you a sense of why we believe GPU is so promising for data analytics, right? And after that, I'm going to show you a demo of a system that we have built. It's called Camelot. It's a GPU database that has really high performance. So we are going to show you how Camelot compared to DuckDB, which is a very fast CPU database. So with the demo, you have a sense of how fast it can be. And then after that, I'm going to spend more time on the specific optimizations or technologies we developed for GPU databases. Okay. All right. And by the way, I'm happy to take questions during the talk. So if you have any question at any point, feel free to raise your hand, or you can just unmute yourself and directly ask the question. Okay, so we know GPUs are really great for like massive parallelism, right? Compared to CPU, which may have maybe 32 cores, 64 cores, and maybe really parallel GPU has 128 cores, but GPU has way more parallel threads, right? It can go to thousands or even 10,000 parallel threads. And all of these threads will perform very similar operations. And they have a single instruction, multiple thread model. And the threads have relatively simple control. Well, that's why they can fit so many threads on a single chip, right? So the thread cannot do really complex stuff. And the threads are mostly independent. So you cannot really do a lot of synchronization for GPU threads because of the performance overhead. Well, if you ask, well, GPU is great for these applications, but what about data analytics, right? So does data analytics have all of these patterns so they can be accelerated in GPU? And luckily, it is true, right? If you think about the like SQL queries, like selection, projection, join, they are all massively parallel. You pretty much do the same operation for every row in your table, and you have millions to billions of rows, and they all perform in similar operations. So that's actually a perfect match for the GPU architecture. And so in a prior work we did a few years ago, we showed that if you fully optimize GPU query processing to the extent that it can saturate GPU memory bandwidth, you can get 10 to 25 times speed up compared to CPU. And this performance benefit fundamentally comes from the fact that GPU has higher memory bandwidth than CPU. So if you look at the architecture between GPU and CPU, we'll see GPU has several major advantages for very fast data analytics. The first one is that the GPU has very high computational power inside the cores because it has so many threads and single instruction multiple thread execution model. And the second advantage is that GPU has really high memory bandwidth, right? So a CPU memory bandwidth, we're probably talking about 100 gigabytes per second. But for a GPU, we are talking about terabytes per second. Like the fastest GPU today is 5.2 terabytes per second memory bandwidth, which is like 50 times higher than the CPU. This is another reason. This is actually the main reason why GPU is so great for data analytics. And if you look at the hardware trend, um, in the last, this shows the GPU computational power in terms of giga floating point operations per second. And this showing you the data like for the last 10 years. So we can see 10 years ago compared to today, it's like 30 times increase in computational power. And just for the last 4 years, the GPU peak performance has increased by 5x. And we can see the same trend for GPU memory bandwidth. So while 10 years ago, GPU memory has pretty low bandwidth, although this was still much higher than CPU memory bandwidth, is like 300 gigabytes per second. But if you look at today, it gets to terabytes per second. And just for the last 4 years, that increased more than 3 times, right? So you can imagine if this trend continues, within a few years, like the performance gap between GPU and CPU would keep widening. And at some point, if you care at all about fast data analytics, you probably don't even have a choice. You have to use GPU if you want to get performance at all, right? Because if you write a GPU database, the performance will keep increasing as the GPU hardware improves, right? But the same thing may not be happening for CPUs anymore. Okay, so although GPU has really high computational power and memory bandwidth, but there are also some challenges to run data analytics on GPU. So the first challenge is that the GPU has very limited memory capacity. So while a CPU memory can be hundreds of gigabytes or even terabytes, but the largest single GPU device has only less than 200 gigabytes memory. Like um, I think H100 has 80 gigabytes, and this biggest GPU has 192 gigabytes. So that's relatively small. So that means if your workload is large, then it does not fit into your GPU. And another limitation, which um, is the other side of the story, is that the interconnect between the CPU GPU is also very limited. Right? You can say if the GPU memory capacity is small, but if the interconnect is fast, well, that's still great because you can store your data in CPU and keep reading it. But now your PCIe bandwidth between CPU and GPU can also be relatively limited. So, well, your data, you cannot put a lot of data in GPU, and you also cannot load data very fast into GPU, right? So that becomes a bottleneck. Well, however, even though these are challenges, but the situation has been improving a lot for the last few years, right? If you look at the GPU memory capacity, within the last 5 years, it has increased by 6x. So it used to be, I don't know, only 32 gigabytes, but now it's 192 gigabytes. And this is the bandwidth between CPU and GPU. It pretty much doubles every 2 years. Right now, we already have well, if we are talking about PCIe 5 or 6, it's already 32 or even 64 gigabytes per second, which is getting very close to CPU memory bandwidth already. And furthermore, um, within GPUs, there is a connection technology called NVLink that can give you hundreds of gigabytes per second. And that has also been increasing rapidly in the last few years, right? And another thing is NVIDIA has been developing a new interconnect between their own CPU and GPU. And there they can use the NVLink. So with that technology, maybe the bandwidth limitation between CPU and GPU can also be resolved. Right. So with all of these trends, we feel, okay, GPU is, if you really care about performance, maybe a GPU is the only choice going forward. Okay, so any question so far? Okay, yeah.
I have one simple question regarding is there any comparison between GPU and CPU like based on the data size where the performance is invariant?
You mean for different data size, the performance invariant?
I mean, when should one consider that, okay, now CPU is not sufficient for me because of the data size or because of my
Oh,
query? Like, when should one decide that now I have to move from CPU to GPU? Is there any like thumb rule for that?
well, I guess is a performance. Like if you have a query and you want to finish it with like 10 seconds versus 1 second versus 0.1 second. I think if you want a shorter time, you want a higher performance, then that's when you move to GPU. That's one way to think about it. But I guess there are probably multiple reasons. For example, when would you want to use a faster CPU? Like, what will trigger that decision that you will want to switch to a
Right.
faster CPU? You just want a better performance. You want a better experience. There's no simple answer to that. And GPU, I think, is the same. It's just a faster software, it's a faster database.
I see. Okay. My view was that like for probably for small data, we probably don't need GPU. CPU is sufficient, but for cloud or data center where the load is higher and concurrent access, and there are many customers or clients are using server, probably that's where performance makes sense. I am just saying my thoughts, nothing else.
Yeah, that's probably true. Yeah.
Thank you.
You have another question?
Yes. So if, although I think that GPUs have much more memory bandwidth compared with CPUs, they also have much more threads. So if the threads actually try to touch random accesses in the memory and they do it too much, doesn't it actually make it slower than the CPU? Because it's even though the memory bandwidth is much more higher, the number of threads are actually much more higher than CPU.
I mean, this is completely orthogonal. In CPU, you also have random memory access. So it's not like this is the random memory access is only problem for GPU, but it's also a problem for CPU, right? So if you have a lot of threads, what you are saying is because you have too many threads, maybe that this high memory bandwidth is still not enough to keep all the threads busy, right? Because if you hit the memory bandwidth bottleneck, then maybe half of your threads are not doing anything, just waiting for the memory responses. But that's totally fine, right? Because that means, okay, I'm processing 5 TB per second. Well, I'm not saturating my computational power, but I'm processing 5 TB per second. And in CPU, you need 50 CPUs in order to process 5 TB per second. And you get a 50x speed up. Uh, well, sure, you're not fully using your computational cores, but you get 50x speed up. Like, which one is more important? Um,
Yeah, I get it. Thank you.
yeah, thanks. All right, I think we can move on then. So the next step I want to do is before I talk about the technical details, let me show you a demo. And this is the system we have been building. In the front end, we use DuckDB. So the interface looks like DuckDB. So we use the query parser, the query optimizer in DuckDB. But after that, instead of using DuckDB execution engine, we implement a GPU execution engine called Camelot. And actually, when we execute, we use both. Like it's a hybrid execution model. So some queries will run in DuckDB, but some other queries will run in Camelot. And we have a LLVM code generator to generate the GPU code real time and then run it. Okay, so let me share with you this. I have a video, so this is not really a live demo. Uh, my student, okay, let me see where. Yeah, my student made a video. And let me know if you cannot hear things clearly.
Hello everyone. In this video, I'm going to give a demo of performance comparison between DuckDB on the left-hand side of the screen, and Camelot version 0.1, which is the very initial version of Camelot, on the right-hand side of the screen. The setup for this demo can be found on the screen. So the queries that I'm going to run is a prepared statements. So I name it as Q1, and these prepared statements will do a bunch of joins, filter, group by, and aggregations. So first, let's run it and with DuckDB. I'm going to execute Q1, and then we pass in the parameters for the prepared statements. Let's say the parameters is 1101. So I'm going to run it several times so that it's warmed up, but we can see that this takes like around 500 milliseconds with DuckDB. So now let's try to run it with Camelot with GPU accelerations. I'm going to run the exact same query. And since Camelot is using a code generation technology, what we can do is that we can actually precompile these prepared statements so that we can generate a very efficient GPU machine code. And therefore, we can just execute Q1, we will use run Q1, and then we make sure that we pass in the same parameter as the one we pass in with DuckDB. I'm going to run it one more time so that it's warmed up. But you can see that it takes around 5 milliseconds here, so it will be around 100 times faster compared to DuckDB. So that is the demonstration of Camelot. Hopefully, it can demonstrate how fast Camelot can be compared to DuckDB. Thank you for watching.
All right. I think this is actually a good time to ask questions, if you have any. I'll go back to share the slides. All right. Right. So, okay. So now I'm going to talk about some of the research work we have been doing in the last several years to make this happen. Right. Actually, many of these techniques has been incorporated into this demo, but not all of them are. Okay. So we are still actively developing the system to incorporate all of these optimizations and hopefully even more optimizations that we're going to develop. Okay, so I'm going to start about, I'm just going in this order and talk about all the work. So the optimizations we developed can be categorized into two classes. The first thrust is to enable large-scale data analytics on GPU. And this is really focused on performance. Like how can we run queries really fast on GPU? That's kind of the first work. And then how can we fit more data into GPU? Like GPU has relatively small memory size. So can we do some data compression so that more data can fit in GPU? Can we do hybrid CPU-GPU execution so that even if the data does not fit in GPU, we can still do substantial processing in CPU, right? And how can we leverage multiple GPUs to do query processing? Because now multiple GPUs, the collective memory size will be much bigger. And the second thrust of our research is on enhancing the practicality of GPU databases. So how to make it easier for people to use it. Regarding that, we have done two line of work. One is to accelerate user-defined function, and the second one is to do code generation. All right. So I'm mainly focused on the first thrust. And I probably spend more time on the heterogeneous CPU-GPU database because I think that's the papers you guys probably have read. But I'll also talk about the other work. Okay, so the first work is Crystal, which introduces a new execution model called tile-based execution. And this is a framework where you can make GPU query processing really, really fast. So I'm going to keep showing a figure like in this slide. And this figure, eventually all the optimization will fit into this figure. So how you read this figure is like the x-axis is the data size. Okay, so if your data size is small, that fit in GPU memory capacity, then your throughput on the y-axis will be really high. Okay, because now your data is in GPU and you're doing the entire query processing in GPU. But when your data does not fit in GPU database anymore, you can either just run everything on CPU and then you have your CPU DB throughput. Or naively, you can just say, whenever I read the data, I just load the data from CPU to GPU through PCIe. So you're just doing that all the time. Well, if you don't do it carefully, that can actually kill performance because that PCIe bottleneck has much lower bandwidth than the GPU memory, right? So in the first paper, our focus is just on the left part. It's just saying when data does fit in GPU, how can we maximize its performance potential? How can we maximize the throughput when data does fit in GPU? And we don't care about when data does not fit for this first paper. Okay, so here's the problem we are trying to tackle for in this first paper. So we found that in the conventional execution model in GPU, they will have multiple kernels, and each kernel will perform one operation. So let's say you want to scan some data, then do some filtering, and then do some aggregation. So what a conventional execution model does is they will run the first kernel to scan the data. They read in all the data, do some filtering, and then they write all the data back to GPU global memory. And then they have a second kernel that read in data from GPU memory again and do some processing and write it back. Right? They can have multiple of these kernels, and everyone will read data in and write it back to global memory. So this causes a lot of traffic to global memory. And a lot of this traffic is actually unnecessary. So in Crystal, we try to minimize this traffic. So what do? Is we try to use the on-chip shared memory in GPU to cache intermediate result. So that for intermediate result, you don't want to write all the way back to GPU global memory. So what you do is you partition your data into smaller tiles such that each tile can fit in the shared memory. So each time when you process, you load the entire tile of data, then you do the scan, you do the probe, you do the sum, all on the same tile. And all of that happens in memory, in shared memory on the GPU chip. And then for the final result, you write it back to global memory, right? So this way you can reduce a lot of global memory reads and writes. And that can immediately lead to a significant performance improvement. So I see there is a question.
Yes. So my question is, who are you talking to? The operating system or a programmer whose program is aware of the location of the data and the execution plan and where the query is going to be executed?
Wait, I'm not getting your question. Can you say it again?
Yes. So what you are telling us is for like who is the audience? Who are you talking to? When you're saying that you mean someone, the operating system. I mean this information that you are telling us is for like data processing that is aware of the machinery layout, or a data processing scheme that leaves the assignment of the memory allocation and processor selection to the operating system. So, for example, if I take a piece of code and run it in different scenarios, would that be different, or I should specify in my code where to, for example, execute my code, where to locate my memory, and when, for example, when you say when the data does not fit in the memory, you have to do this thing and that thing. So how can I know that whether my you're talking about the situation in which the memory should reallocate, the code should reallocate the memory, the data. I'm not sure if I'm.
Oh, Tamer, you're trying to say something, but you're muted.
I think the question is whether it's the programmer who is responsible for this, or is it the execution engine the kernel that does all of this? I think that's the question.
The database developers take care of all of this. We are building a database, and database interface is like SQL. And the database user, they just know SQL, and database developers will take care of all of these.
So this is done by the database kernel.
Yes, the database
execution engine, I should say.
Yeah, execution engine. Yes.
Yeah.
Thank you.
I have just another quick question. Just in the left-hand side, you have 3 kernels, but in the right-hand side, you have 1 kernel.
Yes.
So their kernel, each kernel has some capacity. Are you increasing in the right-hand side the kernel capacity of execution power, or
No. Kernel is, you think of it as a function. Whatever you run in GPU, you need to wrap it into a kernel, and then the GPU can execute it. The kernel, it's like a function. Well, what's your capacity of a function? It can be arbitrary. And the same is similar here. Well, of course, it cannot be too big, but most programs can fit in. All right. So yeah, here's some performance evaluation of the Crystal library. We evaluated several baselines. Hyper is a pretty fast CPU database. Well, I think when we did this work in 2020, DuckDB was not yet popular, so we didn't evaluate DuckDB. But I think DuckDB will probably be somewhere like here. And the standalone CPU is one hand-optimized CPU database we developed. Like it's hand-optimized to the extent that we can almost saturate the CPU memory bandwidth all the time. And OmniSci, well, at that time it was called OmniSci. Now it's called Heavy AI. They are a very fast GPU database, but they don't have the tile-based execution model, so they're not fully optimized as Crystal. Like Crystal is the last bar, but that's almost saturating the GPU memory bandwidth. So it's getting 25 times speed up over CPU databases running SSB benchmark. Okay, so that is the Crystal library, and the focus here is to make GPU kernel processing really, really fast when data does fit into GPU memory. But then the more challenging question is, what if the data does not fit in GPU memory?
I have a quick question, sorry, about the results in the previous slide.
Yep.
Yeah, so I mean, I see that your CPU, it's an i7 CPU, and you're running it on 8 cores, where you have like almost like, I don't know, it's a V100. I guess it's from a GPU from last 5 years. Is it a fair comparison? I mean, I would expect like running it on like a 64 core CPU. Then I would say it's a fair, probably apple to orange comparison. But right now it doesn't seem that way.
Well, if you want a 32-core CPU, you can get a 32-core CPU, and the CPU performance is probably 8 times faster. And the y-axis here is log scale. So yeah, and the GPU will be, in that case, maybe 4 times faster than the CPU implementation.
Okay, yeah.
Yeah. Okay, so when data doesn't fit in GPU, there are, well, hopefully multiple ways that you can deal with that. Like, for example, one technique you can use to compress the data. So after compression, the data will become smaller, and hopefully more data will fit in GPU. So in this work, we apply data compression and we try to optimize the decompression process. Because if you just naively compress the data, and in GPU, what you need to do is you keep decompressing the data all the time before you can process it. And that will potentially waste a lot of computation, right? So for example, this is actually, the first idea in this paper is very similar to the Crystal paper, where if you do conventional decompression, and your compression is always a cascade. Like, it's not a single compression algorithm. You apply maybe run length encoding, and then on top of that, you apply bit packing, right? You always have layers of compression in order to reduce the data size. So conventionally, what you do is you will decompress these layers in different kernels. So you were reading the data, and okay, let's say the data is compressed using delta encoding first. And then on top of that, you have bit packing. And when you decompress, you need to go the reverse order. Right? You first load the data, decode bit packing, and then you write back the result to GPU global memory. And you're reading in the second kernel, you're reading the data again, and you do the delta decoding, and then write it back, and then finally read it in again, and you do the query processing. The query processing is like scan, aggregation, or join. Right. So there is a lot of global memory traffic, like the previous example. And then what you can do instead is, well, a tile-based execution, again, you chunk your data into smaller tiles so that each tile can fit in the on-chip shared memory. So you read in a tile, you do the multiple decompression steps, and you write the data to shared memory, and you read data from shared memory, right? And after all of these decompression steps, you can also pipeline that with the query processing. So you get the tile data and immediately do the query processing, like scan, filtering, and aggregation. And only then you have a pipeline breaker, then you write it back to global memory. Right, so that's the general idea of it, the tile-based decompression. And we also developed some like compression formats specifically for the GPU. Well, we targeted 3 common compression frameworks like bit packing, delta encoding plus bit packing, and run length encoding plus bit packing. And we develop a GPU specific formats so that it can become very efficient, both in terms of memory consumption and also in terms of decompression speed. So decompression speed is more important because the data format developed for GPU may not be optimal for GPU. Developed for CPU, optimized for CPU may not be optimal for GPU anymore. So here are some evaluation results. Well, again, the first baseline is no encoding, no decompression at all. The second one, the third one are some prior work in GPU decompression, so I'm not going to talk about the details. The fourth one, NVCom, is an NVIDIA library that does the compression and the decompression for GPU data. And finally, the last one is our design. So in terms of compression ratio, we are very close to NVComp. Like it's basically about the same. So basically you can reduce the 7 gigabytes of data down to about between maybe 2.5 gigabytes. And in terms of decompression speed, we can be much faster than all the baselines, right? So well, that's because of the tau-based decompression. We can substantially reduce the traffic to global memory. And overall, the proposed design can be 2.2 times faster than NVComp, which is the best previous scheme. Okay, so that's the decompression work. Any questions? Yep.
Is there any time trade-off for the decompression, like from the latency point of view, performance?
You mean trade-off in terms of
Like you are by compressing, you are having more, you can fit more data into the memory,
yes.
but you are doing extra work by doing
Yes.
compression and decompression. So is
Yep.
like, what is the trade-off of this? I just want to know it overall.
Well, I guess certainly you can say it's certainly a trade-off. Whether you want to fit more data into GPU or you're okay with like spending more computation time doing the compression and decompression. I think if you ask me, I would say it's probably always worthwhile to do the compression. It's like when you when you store data on disk or S3, you always do the compression as well. Well, you try to. The benefit is pretty significant. And the decompression, based on our evaluation, decompression can be done pretty fast. So actually, there is a slide I didn't show here, but it is in the paper. There is a result showing after compression, we also compare the end-to-end query execution time. So you can see with compression versus without compression, how does that change the query execution time? And that's actually about the same. Like so, because on one hand, decompression, that's extra computational overhead. But because of compression, you also reduce memory traffic. Like now you need to load less data from memory. So that will help performance. So in our evaluation, we show that actually they're about the same. So in the end, the performance doesn't change much. Of course, if you optimize it more, maybe the conclusion will change a little bit. But the thing is, query execution time is similar, but you can process two times more data in GPU, which is quite attractive.
Right, right. Thank you.
Yeah. Okay. Yeah, so that's the second work on decompression. Well, even after you compress the data, it may still be the case that data does not fit in GPU. Like in this case, if you look at this red bar, now you can fit more data into GPU. So even the larger data set can enjoy GPU acceleration. But still, when your data doesn't fit, your performance will go down. So in this third work, we are trying to say, if your data still doesn't fit in GPU, then you can do heterogeneous processing. So that's part of the query will run in CPU and part of the query will run in GPU. And you can do collective execution so that hopefully you can reach the maximum performance. And then hopefully that's faster than maybe naively going back to the GPU when data doesn't fit or keep transferring data from CPU to GPU. Okay. So we identified two challenges in this hybrid CPU-GPU database. The first one is data placement. Like what data do you put into CPU versus GPU? And the second one is heterogeneous query execution. So if you do have data that some of the data in CPU, some of the data in GPU, then how do you run the query? Now your data are in two different places. And it's not simply like a distributed system question because they are heterogeneous. It's not symmetric. So how do you do the execution? So first, how do you do data placement? And actually, well, like some prior work, we model the problem as a caching problem. So we will assume the complete data set will always reside in CPU memory, but the subset of data can be cached in GPU, right? So even if a subset is cached in GPU, but that subset will still be stored in CPU. So CPU will keep track of all the data. GPU is just a subset. So how do you do cache replacement, right? If you model this as a cache problem, then you can do cache replacement. Well, so let's say this is our two relations. We have R and S, and they actually join, and the join key is column C and column D. So a lot of prior work, they will do coarse grain caching, which means they cache the entire column. They always try to cache the entire column. But let's say if you can cache the entire column A, but well, that column A after cache, you still have some cache capacity in your GPU, but the small space is not enough to cache another column. So in this case, you have some fragmentation issue because you're not fully using the cache capacity in GPU, right? So this will be a waste of GPU resources. And alternatively, you can also do fine-grained caching. So in this case, we say we slice the table R into different row groups. And each block here, a row group for a particular column, we call it the segment. And you can cache multiple segments. You can cache the entire column A, and you say, I still have some space. Let me cache two segments in column B. So you can also do that. So that's fine-grained caching that prior work has proposed, right? But one thing we observed that is the prior work, they mainly use conventional caching algorithm like LRU or LFU. The LFU stands for least frequently used. So basically just say what data is more frequently used, I cache it, or what data is more recently used, I cache it. But they don't consider the semantics of the query. For example, if you think about it, intuitively, the join columns should have a higher priority because if a join column is cached, then they can be accelerated more because join is very expensive. Doing join in GPU give you a much performance boost compared to doing join in CPU. In contrast, doing a selection in either device is probably going to be similar because even in CPU, selection is very fast. And selection is not a major part of your query execution time anyway. Most of the query execution is in join. So what you should do is to prioritize join columns, right? So yeah, the limitation is not aware of the query semantics, and we want to cache the columns that leads to the highest speed up. Right? Caching a selection column give you speed up, but not a lot. But caching a join column will give you a much bigger speed. So that is that's the key insight behind this work. So basically what we do is we extend frequency-based caching with weighted frequency counters. So we would say, if a segment, for each segment, we just model, well, what is the cost of caching the segment versus, sorry, what's the runtime of caching the segment versus not caching the segment? So the difference between the two is the benefit of caching the segment, and that is the weight we are going to add to the counter for the segment. Yeah, is there a question? You're muted, by the way.
Yeah. In the previous picture, in the right hand side, you have shown like two in the GPU memory, two side colors. Is there any significance for that or no?
GPU memory is one color, though.
One like dark shade of red and like light shade of red, probably
Oh, these two are the same color, column C and column D.
in the right hand side GPU memory, the right of D.
You mean
Oh,
there is one color here?
no, I mean,
It's your monitor and it's your monitor. It's one color. GPU memory is all one color.
oh, okay, so probably it's my memory. Okay, in my monitor it is showing the middle three is more brighter red than the top two and the bottom two. Okay. Hmm. I thought you were like copying the D, which is like the probably the primary key and something like that.
Yeah, well, maybe in the paper is the color differently, but here we're just caching C and D.
Okay.
Yeah. Okay, so to illustrate this idea of this weighted frequency counter, we just say, if, for example, when we consider this segment S, we just say, well, what if this S is cached? Oh, it's not cached. And we just say, if it's uncached, we have a mathematical model to estimate the runtime of the query. And this model actually comes from the sundial, sorry, the crystal paper, where we say if this segment is not cached, then we just model the runtime assuming that execution is going to saturate memory bandwidth. So it's a very simple model. It's very easy to compute. And it's not going to be super accurate because it's assuming you always saturate memory bandwidth. But in the crystal paper, we actually found that is pretty accurate, at least for the crystal library. Okay, and then you estimate what if this segment is cached, and you want to estimate the runtime. So the difference between these two will be the weight of caching the segment. So when you access the segment, you increment for that particular query, you increment the weight for that segment by this value. So, and later you just say, whoever has the higher weight, I will try to cache it. Like, so that means, well, if there is a join column, but if that join column is never accessed or very rarely accessed, that will still lead to a lower weight, overall weight. So it may still not be cached. So this would take into consideration of semantic, and also it will consider the frequency. Yeah, is there a question?
Yes, I just want to know the granularity of the cache, like how big each chunk would be.
I don't remember details, probably a few megabytes.
Few megabytes, and it's just arbitrarily decided, or it's
not very sensitive. Like well, we can cache at maybe 20 or 30, 40 gigabytes of data, and the granularity here is not going to be too sensitive. Like from a few megabytes to 10 megabyte, 20 megabytes is probably giving you a similar result anyway.
Gotcha. Thank you.
Okay, so that is the data placement part. We have the semantic aware frequency-based replacement. And then in terms of heterogeneous execution, well, given a particular data layout, like you decide to cache some data in GPU, and then when you do the execution, you also need to take that into account, like which part of the query should run in CPU versus GPU. And we want to do this and we want to exploit the parallelism in both devices. We want to fully utilize both hardware devices. And we also want to minimize data transfer, right? Because data transfer is, well, it will hurt performance since PCIe has very limited bandwidth. So we want to do this without transferring too much data. So let me show one example. So basically, we introduced that as the idea of a segment level query execution. So depending on the caching behavior of different rows or row groups, then we will apply different query execution model to different row groups. So for example, here, like in relation to R, we have this caching behavior. Like these red segments are cached, but these gray segments are not cached. And this is the query we are trying to execute. We do a filter on relation R. We're reading relation S, and we join these two relations on column B and D. And then we do aggregation in the end. Okay. So the first thing is, because different row groups are cached in different behavior, different pattern, so we will separate relation R into different groups. We say the first two row groups, we put them into group one, and they will have the same execution plan. And the next three row groups, we put them into group two, and they will have their execution will be different from group one because the caching behavior is different. And finally, for group three, nothing is cached. So actually, the data in group three will be executed in CPU. It will not be in GPU. All right, and the different groups will have a different execution plan, and they will also incur different behavior across the two devices. Right. So for example, let's first see group one. So the execution plan for group one will be entirely in GPU. So you do the selection, you do the join, you do the aggregation, and then finally you send the aggregated result back to CPU. Okay, this makes sense because everything is cached, so you can run everything in GPU. But if you think about group two, column A, B are cached, so you can do the selection. You can also do the join. But column C is not cached, so you cannot do the aggregation in GPU. So what we do is after the join, we send the join result back to CPU, and the CPU will do the aggregation. Okay. And finally, for the third group, nothing can be cached, nothing is cached, so we just run the query in CPU. And finally, there is a merge operator that will combine all the different query execution plans, the result from different plans for different segments, and that will give you the final output. The merge is typically not very expensive because this is the query result, and query result is typically small compared to the input data. Okay, so we built Mordred, which is a hybrid CPU GPU database. So at high level, Mordred has a cache manager. The cache manager uses a semantic aware caching model to determine what data should be cached in GPU. And by the way, the cache manager itself runs in CPU. So the logic runs in CPU, and the CPU decides what data to cache in GPU, and the CPU will update the frequency counters, right? Because GPU is not really great for these control logic. So all of those happen in CPU. And then given a particular cache layout and a particular query, we will have this hybrid execution engine to run the query across both devices. And we also applied a lot of the smaller optimizations like late materialization, segment skipping, so that using min-max value, you know this segment will not be accessed, or we just skip it. So we have done some of those optimizations as well to make the performance good. Okay, so this slide summarizes the performance of Mordred. On the left-hand side, we are evaluating different caching policies. So you can see the bottom line, I mean, the y-axis is execution time. So the lower, the better. And the x-axis, we are showing the cache size. So here we are fixing the data size. And this is scale factor 40 for this figure, which is like almost 40 gigabytes. The original data size is like 40 gigabytes. But we are changing the cache size. So when the cache size is very small, pretty much everything happens in CPU because nothing can be cached in GPU. So the performance will be, all of them have similar performance. And when the cache size is very big, everything will be cached in GPU. And the cache replacement doesn't matter because there is no replacement. But when the cache size is in between, you can see that different replacement algorithms will have different behavior. Like first, column-based, like the top 3 lines, column-based replacement will have worse performance because they always cache entire column at a time. And if you have a segment granularity, like more fine-grained caching, you can cache a segment within a column, the part of a column. And that will generally give you better execution time. And finally, semantic aware will give us the best performance because it takes the query execution, well, whether it's a join column, whether it's a selection column, it will take that into account to improve performance. Okay, so on the second figure, we are showing end-to-end performance of different systems. We compare to a few existing systems like CocoaDB, YDB, and again, HeavyDB. That was the OmniSci before. So when we write this paper, they already changed name to HeavyDB. And then finally, Mordred. Basically, Mordred can be about 10 times faster than the best previous design. And this is partly because of our caching policy, is partly because of the hybrid execution model. All right, any question about Mordred?
In the end-to-end performance, the cache size was average, right? In between, middle.
I forgot the size. Yeah, but it gotta be somewhere in between here.
In between, yeah.
Yeah, I don't remember. Wait. Yeah, the cache size for Mordred, it is is probably the largest cache size we can use for that hardware. And by the way, the scale factor here is much bigger, it's 160 gigabytes. Oh, wait, can you hear me?
Yeah, we can hear you.
Okay. So I think the video got frozen. Yeah, but for the baseline, I think I don't know what we tuned. Maybe we just use the default. Like HeavyDB is actually a commercial system, it's open source, but we probably just use the default. So they will set the size.
I see. And only Moderate is using the semantic error, right?
Right. We didn't. It's very hard to implement this in another code base. Yeah. So there is another question.
So can I ask a question about the paper itself?
Yeah.
In the paper, it was said that Cache Manager actually partitions the GPU memory into data processing region and data cache region, and data processing region is used for generated intermediate data. So, is there a possibility that we run out of memory because of our limited data processing region? And if that happens, what happens? Do we get an error? Does Mordred crashes or?
That's a great question. So I don't know what actually I do have this. So yes, we partition the GPU memory into data processing and the cache. Right now, I think in our current prototype, we don't do anything sophisticated. So if you run out of memory, GPU memory, maybe it will crash. But you can say, if you want to build this in practice, there are many solutions you can use. For example, well, the naive approach is just fall back to CPU execution when you run out of GPU memory. And you know you're going to run out of it. You just say, okay, let me run this query in CPU. Or you can say, oh, you know what? I just evict my cache. I just say, okay, I need to finish this query. That's the highest priority. So let me just start to evict stuff from my cache so that I can finish the query. It's like you steal capacity from the cache region to the data processing region. So you can do sophisticated policies like those. Yeah, but in our current implementation, it's static.
Thank you.
Yep, thanks. All right, so that is for Mordred. I guess I have some time to quickly go through the last few pieces of work. These are not, well, at least for the next one, the multi-GPU DBMS is not published yet. So I will quickly go through that. But the idea, like the intuition is very simple. Like a single GPU can only support a small data set. And if you have a larger, well, you have 4 GPUs or 8 GPUs, then you can easily store much bigger data set in the aggregated memory capacity. So yeah, in this work, we try to enhance Mordred, like the heterogeneous CPU GPU database, to support multiple GPUs, right? So we will first treat multiple GPUs as a unified GPU. So we treat it as a single GPU, but it's actually multiple GPUs. But when treating it as a single GPU, this will be the same architecture as Mordred. So we can use the Mordred cache replacement policy to decide what data should be cached in this unified GPU and what data should be executed in the CPU, and like when you do execution, what part of the query plan should be executed in GPU and what query plan should be executed in the CPU. So you can use whatever we developed in Mordred to make that level of decision. But then after some data you decide to cache in GPU, or you decide to run part of the query processing in GPU, and now it matters like which GPU you put the data into, right? So we kind of do this 2-level decision making. You always treat it as one GPU first and make some replacement or caching or execution decisions, and then you zoom in and decide how to coordinate among multiple GPUs. So at a high level, we build this system is very similar to Mordred in terms of the architecture. There's a cache manager, there's a query optimizer, and the query execution engine becomes more complicated because you have multiple GPU. It's like a distributed system by itself. And we have done a bunch of optimizations here. Some of those are similar, is very similar to the Mordred paper, but there's some more optimizations specific to distribution. Okay, so here's some performance result. On the left, we show the scalability to multiple GPUs. So different lines represent different number of GPUs. So from 1 to 2 to 4 to 8. And you can see the throughput improves. And on the x-axis, we show the scale factor. So the data increases, right? So when the scale factor is very small, the data fit in GPU, even it will fit in even a single GPU. But as you increase the data size, it does not fit into a single GPU, so performance degrades because you do a lot of processing in your CPU now. But you have 2 GPU, more data will fit in GPU, but then again, performance goes down. So basically overall, when you double the number of GPUs, performance will well, maybe not exactly doubles, but performance improves. And especially like when data is very small, more GPUs will certainly lead to better performance, but this effect will become more significant when your data is large. Because when data is large, it does not fit into 1 GPU or 2 GPU. So, but it does fit into a GPU. So that's why you can see a much, much bigger performance gap between 8 and 1 and 2. Yeah, is there a question?
Yes, I just have a question about the previous slide.
Okay. This one?
Oh, sorry, not the one before this one. Yeah, so I just wonder if the semantic awareness is also employed if for the multi-GPU architecture.
It is.
Like for example, for like for doing like hash joins, like since it's very expensive, then it will be better to have it perform like have the work done on 1 GPU rather than have it distributed over multiple GPUs. So that's so I guess the algorithm is aware of that then.
So okay, interesting question. So you're saying compared to a single GPU, in multiple GPUs, it's harder to estimate the execution time. Therefore, it's more difficult to do semantic aware caching. Is that the question?
Yes.
But well, the thing is, you don't need to be you don't need to be 100% accurate in your estimation. Okay, your estimation just need to be accurate enough so that it reflects the runtime difference, but that doesn't have to be super accurate. So that's why treating it as a unified GPU helps. You can simply say, I have a 1 GPU. I don't care about like the 4 GPU data transfer, etc. It's too complicated. I just assume it's one giant GPU, which is, I don't know, the performance is the memory bandwidth is 4 times bigger than a single GPU, and the computational power is 4 times bigger. And then you just assume that virtual GPU, and you just estimate cost on that virtual GPU.
Gotcha. So
yeah, that is easy to do, right? That's like exactly the same as Mordred.
Oh.
And then when you actually need to talk about distribution, then you zoom in. But in the semantic aware caching, at that step, you don't worry about distribution.
Gotcha.
Yeah.
Thank you.
Okay. Yeah, we also have some end-to-end performance. We show the execution time compared to some prior work. A Lancelot is this paper. A Mordred is the previous paper. So having multiple GPUs can beat, like Lancelot performance can be much higher than Mordred. Well, that's expected. And HiveDB here, we also use multiple GPUs. Like HiveDB does support multiple GPUs. So when you do use multiple GPUs, HiveDB can outperform Mordred because Mordred uses single GPU, right? But Lancelot is still much faster. We also have another experiment where the data doesn't, sorry, this data does fit into GPU, this figure. But when your data does not fit in GPU, lens slots will still have very good performance. But in that case, HeavyDB will run the query entirely in CPU. So the performance gap will be even more. Okay. So that is thrust one. And that's the main part of my talk. So I'm probably not spending too much time on thrust two. I'll probably skip a lot of it. But this one paper, maybe I really quickly go through it. Its basic idea is a user-defined function. User-defined aggregation function is actually very slow in GPU. And I will not go into the details. Basically, we use tile-based execution and compilation to make it much, much faster. Again, I don't have time to go through the details. And this has led to 8,000 times speed up. And this is really because the baseline was not fully optimized. And this feature has been integrated and released into NVIDIA Rapids cuDF with this specific version. So this is, you can go to their open source system and you can, it's already having our optimization integrated. And the last thing is we're working on code generation. This is completely ongoing work. This is a very early initial stage. So we already have this demo. The demo has some code generation embedded, but there's a lot of extra work we have to do to fully to fully leverage the performance benefit of this. Okay, so this is my last slide. With all of these and especially the hardware trend of GPU devices, we feel GPU is becoming the new modality of SQL analytics. So we have done a series of work to push the performance of GPU databases to make it faster on single GPU, to support compression, to do hybrid CPU GPU processing, and now we do hybrid CPU multi-GPU processing. Right. So with that, I'm happy to answer questions. Thank you.
Thank you very much, Xiangyao. If there are any questions, there's one.
One and again very quick question regarding so as you said that you have GPU and the CPU model and you have multiple GPUs. Is there any way, say like for example GPU, we always study CPU utilization, right? Computation and memory utilization. So if one of the GPU or multi GPU is less utilized, is there any way multi CPU can share GPUs?
Multi CPUs share GPUs. Well, I think that's okay. In some sense, that's kind of the case today. It depends on what you're referring to. Like a lot of servers have multiple sockets.
Mm-hmm.
So when you talk about the one server, usually there is multiple CPU chips.
Right.
So in that sense, they can share the GPU because they have the one PCIe connection to GPU. And maybe you're thinking more about you have multiple servers. Can they share GPU?
Or multi GPUs, where the architecture is shown in the right hand side, where
Oh, the
four
multi
GPUs.
GPU, what people do is they have one CPU island where they may have multiple sockets.
Mm-hmm.
Then they have PCIe. Then here they can have a GPU cluster.
Okay.
So they can have, I think they can go up to 32 GPUs. Maybe now the number is even bigger. It's very expensive though. But you can put a lot of GPUs connected using NVLink and then connected to one CPU server, right? That is possible. But if you have multiple CPU servers,
Right.
they sharing a GPU cluster, that I'm not sure.
Okay. Yeah.
Because now you have multiple PCIe. I mean, what does that mean? So I think that's the less clear to me. Yeah.
Okay. Right.
I suspect, Xiangyao, if CXL becomes available, that
Oh
kind
yeah.
of setup is going to be easier. But
right, with
right now,
CXL,
it's a challenge. Yeah.
yes, CXL may solve this problem.
Yeah. Yeah.
Yeah.
Any final questions of Xiangyao? All right, I think we're all done. Thank you very much again, Xiangyao.
Thank you.
Much appreciated. It's a very nice talk.
Thank you very much.
We'll see you somewhere soon.
Yeah, see you.
Take care.